All right, let's get started. So last class, we introduced this idea of alpha carbon chemistry. We actually haven't talked about any chemistry of it, but we talked about that alpha carbon, right? The one located right next door to the carbonyl carbon in our aldehyde or ketone. And the thing that makes that alpha carbon relatively special is that that hydrogen that is bound to it is relatively acidic. We can remove that hydrogen, all right? This is going to be the key to understanding this alpha carbon chemistry business. And thus far, we've only really talked about one sort of example of that, what's called this ketone-enol tautomerization, right? An internal arrangement of aldehydes and ketones to form an enol. We can see that we just kind of pick up that hydrogen, that relatively acidic hydrogen, and move it over to our carbonyl oxygen when we create our enol. And this reaction, the equilibrium very much so favors our ketone, but that doesn't mean that it's not going to be important. In fact, this is going to be a really important intermediate here in our reactions. All right, and we illustrated that under acidic conditions. We did the mechanism here, showing that in order to avoid any sort of negative charges, any strong bases, we're going to first protonate that carbonyl oxygen, and then we can have our elimination type reaction to form our new carbon-carbon pi bond. Okay? Cool. So now we're going to look at some reactions here. And that enol is going to be an important factor in this reaction here, what's called alpha carbon halogenation. Right, so if we take an aldehyde or ketone and we combine it with a halogen in acidic conditions, as the name here implies, we're going to see that our alpha carbon gets halogenated. We get that bromine on our alpha carbon. Right? Not our carbonyl carbon. We're not talking about carbonyl carbons being electrophiles anymore. We're talking about our alpha carbon. All right, so why is that? Well, again, we know that under this acidic conditions here, we have this tautomerization. All right, and when we have this tautomerization, we get an alcohol right next door to an alkene, to a carbon-carbon double bond. All right. And kind of just ignoring the presence of that alcohol group for a second. We discussed alkene chemistry quite a bit. And what do we know about those pi bonds? Do those pi bonds play the role of nucleophiles or electrophiles? Nucleophiles, they are themselves electron rich. And so that pi bond is going to react just like we saw with alkenes, going to reach out and react with that bromine. All right, now carbon, if we just stopped here, we would have carbon form a carbocation, which isn't illegal under our acidic conditions, but it's not really preferable in the sense that carbon doesn't want to break its octet. Remember, carbon's a weird atom in that when it forms that positive formal charge, it has to break its octet to do so. So there's a way more stable way that this reaction can hold that positive charge, and that is if simultaneously that pair of electrons comes down. And notice that that is going to direct that bromine specifically to that alpha carbon, right? It doesn't give it a chance to react with that carbonyl carbon. It's going to force it onto that alpha carbon. All right, whoops, not two. So at this point, we've sort of reformed our ketone here, but we have that proton on our oxygen. So everybody take a second and finish this reaction mechanism for me to give us our alpha halogenated product here. Alright, so we need to remove this proton, so we need a base. What should we use for our base? Water. Yeah, every once in a while you'll see people use a bromide ion because that gives you your nice balanced chemical equation with your other product, but truthfully, bromide's not accepting protons. They're terrible protons. They're the weakest bases you could have. So although that gives you your nice, neat, balanced chemical equation, it's kind of not the best way to be thinking about it. What's actually going to be doing the proton accepting here is just going to be one of our water molecules. All right, so the key here is that under acidic conditions, we form that enol. And importantly, now we're seeing our aldehyde or ketone not playing the role of an electrophile in a reaction. It's not accepting pairs of electrons. With our alpha carbon chemistry, now it's playing the role of a nucleophile. It's doing the attacking. All right, so we had to create that enol in order to make our alpha carbon nucleophilic. That then attacks that bromine, and we get this alpha carbon halogenation. Okay? All right, one thing that I think throws people off is the idea that I said this equilibrium favors this ketone here, right? Great, that means that if you were to take a snapshot of that sample, 99.999% of molecules are going to be in this ketone form here. But that 0.01% is going to then go on and form a productive reaction moving forward, right? So it doesn't matter if you have a teeny tiny population. That's kind of all you need to get your reaction going. We talk about protonating these carbonyl oxygens all the time. It doesn't mean that, like on pencil and paper, it looks like everything gets protonated. No, no, no. There's only a teeny tiny fraction that's in there being protonated. But the point being, that's your productive step forward that leads you to the product side, okay? So same thing here. This equilibrium does not very much so favor the enol, but we do get a little bit, and that's enough to carry this reaction forward. All right, but just to go back, we're going to make a big stink out of this here. Our carbonyl carbon, we know, is an electrophilic site. What we're going to see is the theme for this alpha carbon chemistry section is that our alpha carbon plays the role not of an electrophile, but of a nucleophile. Right, so these aldehydes and ketones, they have both an electrophilic site, that carbonyl carbon, but they also have a nucleophilic site, that alpha carbon. All right, and it has everything to do with the fact that that alpha hydrogen is relatively easy to remove, relatively acidic. All right, so keeping on with this alpha carbon halogenation business, we started out our first example with a symmetric ketone here. So it didn't matter which side I chose, I would have gotten the same product. All right, now let's play the same game here, but with an asymmetric ketone. All right, and I guess specifically what we want to discuss, we can title this. This is going to be the regioselectivity of this alpha carbon halogenation. All right, we got two different sort of possibilities for our product here. We could either halogenate the carbon on the left, or we could halogenate the carbon on the right. And we would get two distinct products, depending on which carbon that bromine was directed to. All right, and I'm going to tell you, we only actually get one of these two products here. All right, we don't get a mixture of both or anything like that. This reaction is regiospecific. It's going to prefer one of these carbons over the other. And in order to figure out which one that is, I want you all to take a minute and to draw me the enol intermediate for each of these reaction pathways here, right? We would have a different enol for either of these two reactions. So draw that enol for me. Let's take a look and see if we can't figure out which is going to be preferred in this reaction. So, if we took this top pathway here, and we're going to form our enol. All right, that means we got an OH up top, and now our double bond is over here on the left-hand side. And if we were to, whoops, let me put in my extra lone pair. And if we were to instead get our other product, what would our enol be? Same sort of idea. We also have an OH group, but now my double bond is over here on the right. So looking at these two intermediates here, which pathway do we think is going to be preferred? The top or the bottom? Why the bottom? More substituted alkene, absolutely, right? We just have a way more stable enol intermediate in the bottom pathway than we do in the top pathway. All right, so this top one here, we're not going to see any product. So our more substituted enol, that implies our more stable intermediate. Cool. So it turns out that these alpha carbon halogenations, you can carry them out under acidic conditions, as we've seen here. You can also carry them out under basic conditions. All right. So last class, what we ended with was doing that same ketone enol tautomerization, but under basic conditions. Okay. And the key here is going to be this middle step right here. All right. Our end product we call our enol. This thing in the middle, though, is going to be kind of the superstar of pretty much the remainder of this chapter here. And this thing is what's called an enolate ion. Right? Enol, because it's got that same oxygen next to an alcohol group, but it's not an alcohol group, it's an enolate because it has a negative charge on it. All right, and enolates are good alpha carbon nucleophiles. All right. The halogenation reaction is really the only acidic conditions reaction that we're going to study for this chapter. Everything else is under basic conditions because it features this really good nucleophile right here, the enolate ion. And this particular resonance form right here really helps to illustrate why this thing is called an enolate, because again, it looks like a deprotonated enol. All right, but there's a resonance contributor that's even more important towards understanding why this is such a good nucleophile, and that is if we bring this pair of electrons down here and this pair over to this carbon, you see that our enolate is really just a resonance stabilized carbanion. All right, now to be clear, these are just two resonance contributors. These aren't different molecules. We would put them in a box. We use our double-headed arrow here, right? They are both different representations of this enolate ion. The one on the left, I think helps you better understand why we call it an enolate ion, right? It's just an enol that's lost its proton. But on the right-hand side here, this resonance form really helps to illustrate what we've been saying. Our alpha carbon is a nucleophilic site. All right, you can see it's got a bunch of electron density there. It's got that lone pair on it. So our alpha carbon is a good electrophile here. Cool. All right, so let's just look at our alpha carbon halogenation, but under basic conditions. We have our aldehyde or ketone that's going to tautomerize and form that enolate ion. You can use either resonance structure for your enolate ion, but if you use the one with the carbanion, it's a little bit more straightforward in terms of your mechanism. All right, now you can see that this thing is a great nucleophile. It's got carbon with a negative charge. And that pair of electrons is just going to play the role of a nucleophile and attack that bromine. All right, so Br2, basic conditions. We don't have quite as many steps in our mechanism here. We don't really have to worry about it because it turns out that we don't have that same sort of charge management problem. Just after that one step, well, after we form our enolate ion, of course. Boom. All right, now, of course, I got to complicate things a little bit here. It's not quite that straightforward. It turns out that when you have these brominated alpha carbons under basic conditions, all of a sudden, we said that this was our tautomerization. All of a sudden, that same tautomerization equilibrium now favors that enolate form even more strongly. The presence of the bromine on the alpha carbon will help stabilize negative charge on that alpha carbon. So this thing has no problem reacting with another molecule of base to form yet another alpha carbon enolate ion. Right, so let's just kind of zoom in on this step and make a note that with Br on that alpha carbon, the enolate is even more stable. So it can react with another molecule of bromine. Now we have two bromines on there. And what do we think is going to happen to the stability of that enolate ion when we put two bromines on there? Now it's even more stable. So now our equilibrium favors that enolate ion even more. All right, so et cetera, et cetera, et cetera. The bottom line is that when we have these halogenation of our alpha carbon under basic conditions, you don't just have one reaction. It's going to keep on going and going and going until you have substituted every single one of your alpha hydrogens here. Bear with me. We're going to make a slightly different example. We're going to do pentanone. I'm going to make a point here. All right, but we're going to replace every alpha hydrogen with a bromine. So let's just say our alpha carbon halogenation under basic conditions, all alpha hydrogens are replaced by halogens. And now we got to add one more kind of caveat here, specifically for what are called methyl ketones. So, for example, a methyl ketone is any ketone where on one side of that carbonyl is a methyl group, aka one of your alpha carbons is a methyl carbon. Right? And if we react this with our halogen under basic conditions, it's going to react, but then it's going to react again and again and again. And I'm specifically going to focus on this methyl carbon for right now. Because once it gets to this point, something weird happens. All right, importantly, this carbon, once it's been fully brominated, once it's got these 3 halogens on it, all of a sudden, those halogens, being their good electron withdrawing groups, through induction because they're nice and electronegative, this is now a good leaving group. And remember, we got a whole bunch of these hydroxide ions floating around. And what do we know about our carbonyl carbon? Is it an electrophile or a nucleophile? an electrophile, and hydroxide is a strong base, but also a strong nucleophile. So what's going to happen is that hydroxide is going to attack that carbonyl carbon. All right, this is the same sort of step that we've always seen with nucleophilic attack of that carbonyl carbon, where our carbonyl carbon gets attacked and then that pair of electrons jumps up onto that oxygen. Okay. But here we have something that we haven't seen before, and we're kind of going to see it a lot going forward here. But we have this same sort of intermediate we've seen a whole bunch, what we call our tetrahedral intermediate. We call it a tetrahedral intermediate because that carbonyl carbon went from being trigonal planar to tetrahedral. But now our tetrahedral intermediate has something that we haven't seen before, which is this good leaving group. All right, and so what's going to happen is that pair of electrons on that oxygen is going to come back down and kick off that leaving group. So at the end of the day here, we're not left with that halogenated alpha carbon. We're instead left with a completely different functional group, a carboxylic acid. All right, this is actually a pretty elementary chemical test that was developed for methyl ketones. You can test to see whether your particular aldehyde or ketone is indeed a methyl ketone by reacting it with bromine under basic conditions, because if so, it will form a carboxylic acid. All right, now, everybody's probably got a really good question, which is like, okay, well, what about this other one over here? You kind of completely ignored this. All right, truthfully, there's probably going to be a mixture of products where some of them have a bromine on this other alpha carbon, but importantly, after this step here, any sort of bromination of an alpha carbon will stop. It doesn't happen with a carboxylic acid. We don't have the same game that we're going to play with a carboxylic acid that we do with an aldehyde or ketone. So for the sake of simplicity here, we're going to say no halogens on our other alpha carbon. All right, so this is unique to these methyl ketones. These will react with bromine under basic conditions to form carboxylic acids. Right, so that's because when we brominate that methyl carbon, when we get up to those 3 halogens on one carbon, all of a sudden it's a good leaving group, right? It's got enough of this stabilization from those electronegative bromines to stabilize it, holding that negative charge. And so yeah, that thing's just going to go flying off under basic conditions. All right, so specifically, all right, so just to summarize, under acidic conditions, we get this monobrominated product, and we got to pay attention to which carbon it's going to go on, right? Depending on which enol intermediate is formed, we're going to see that the bromine goes on that more substituted carbon. We can carry out the same reaction, but under basic conditions, and we will see that all alpha hydrogens get replaced by halogens, right? It just keeps on going and going and going. And then specifically, if we use a methyl ketone under basic conditions, what we're going to see is a carboxylic acid is formed because that methyl carbon gets completely brominated and thus is a good leaving group, gets kicked off by that OH. Cool. All right. Another reaction for these aldehydes and ketones is what's called an aldol addition or condensation reaction. All right, what we're going to do is we're going to take a sample of aldehyde or ketone, and we're going to add in some base. All right, and these reactions kind of really hammer home what we've studied about our alpha carbons thus far, or really about aldehydes and ketones period thus far, is under basic conditions, we'll get a small population that forms that enolate ion. And again, that enolate is what? A nucleophile or an electrophile? A nucleophile, specifically that alpha carbon, is now a nucleophilic site. Well, if we have a beaker of acetone, we don't just have one molecule floating around, we have a bajillion, right? And so even though a small population forms that enolate ion, most of them are just sitting in that normal ketone form. And what do we know about the carbonyl carbon of an aldehyde or ketone? It's an electrophile. All right, so here's a reaction between two ketones where one of them is going to play the role of the nucleophile, specifically at that alpha carbon, and the other one's going to play the role of the electrophile, all right, specifically at that carbonyl carbon. All right, so let me kind of try to clean this up so we can do a mechanism here. Okay, given what we've discussed about aldehydes and ketones and about nucleophiles and electrophiles, all right, I want you all to see if you can't figure out what should be the next step of this mechanism here. All right, so I'm going to have my nucleophile attack my electrophile. That's what nucleophiles do, right? They attack electrophiles. And then I'm done there? No, I'm going to always form that tetrahedral intermediate by kicking that pair of electrons up. All right, but importantly now we have this new bond that's formed between the alpha carbon of one ketone. So notice that my nucleophile retains its carbonyl bond. All right, so now here's my new bond. This must be my electrophilic carbonyl carbon here. Well, I got to draw those other two carbons that it's bound to. All right, as well as that alkoxide negatively charged oxygen. All right, and then the last step here is just going to be to make that oxygen happy by protonating it. Consolidate room. And so what we get at the end is what's called an aldol. Even though it's really a ketone and an alcohol together, these are what are called aldols. All right, so we have this sample of ketone or sample of aldehyde, and we just add in a little bit of base. And what that's going to do is it's going to create a small population of these enolate ions, which are nucleophiles. And they're going to react with what is the much larger population of intact aldehydes and ketones, which are good electrophiles. Right, so I have one molecule of acetone playing the role of the nucleophile, another molecule of acetone playing the role of the electrophile, and we get this aldol product at the end here. All right, where we've now connected, we've drawn a new carbon-carbon bond between the alpha carbon of our nucleophile and the carbonyl carbon of our electrophile. All right, so here's my new carbon-carbon bond. And then we just protonated that alkoxide ion to make it an alcohol, giving us our aldol, which really should be like a ketol or something like that, but they call them aldols. Cool. All right, so for the sake of practice, let's pick a different sample of aldehyde or ketone. Let's do butanal. I'm going to take this and I'm going to add in a little sodium hydroxide, and I want to know what my aldol product is. All right, and the easiest thing I think to do is to draw a second molecule of that aldehyde in this case, so that you can see one of them is going to be reacting with its neighbor. All right, again, one of them is going to play the role of the nucleophile. The other is going to play the role of the electrophile. right, so importantly, the reason why one of these is playing the role of the nucleophile is because it forms that enolate ion with its little meh face on that alpha carbon. And that is going to attack that electrophilic carbonyl carbon, forming our new carbon-carbon bonds. Now, just like always when we have reactions that form new carbon-carbon bonds, our products are going to be a lot uglier than what we started with because they got more carbons. All right, and in this particular case, I don't know, they're kind of particularly ugly here. But here's my alpha carbon of my 1. So on the other side, this must be my carbonyl carbon of my neighbor here. So I got an OH group on one side. In this case, it was an aldehyde, so I have just these other 3 carbons to account for. 1, 2, 3. All right, but here's my aldol product that I get with my new bond between my alpha carbon of my nucleophile and my carbonyl carbon of my electrophile. All right, notice that the nucleophile's carbonyl group remains intact, but because the electrophile's carbonyl group got attacked, it turns into a hydroxyl group. Cool. All right, we'll pick up with that next time.